1.2. Combining functions, shifting and scaling graphs. The outline of this video is as follows. We will discuss three main ways to work with functions. First, we will explore composite functions, which is a method for building a new function by plugging one function into another. This is a fundamental technique for modeling multi-step processes. After that, we will turn our attention to transforming the graphs of functions. We will start with shifting, learning how to move a graph vertically up or down and horizontally left or right by making simple algebraic changes. Finally, we will cover scaling and reflecting graphs. This includes how to stretch or compress a graph and how to flip it across the x-axis or y-axis to change its orientation. Mastering these tools will give you a powerful visual and algebraic understanding of how functions behave. We can build new, more complex functions from simpler ones using the basic arithmetic operations of addition, subtraction, and multiplication. The key principle here is that for any of these combinations to be valid, the input value x must exist in the domains of both original functions, f and g. This shared input space is called the intersection of their domains. To find the output of a combined function, you simply perform the operation on the individual outputs. For example, the sum function, written as the quantity f plus g of x, is found by calculating f of x and g of x separately and then adding those two results. Similarly, the product f times g of x is just f of x multiplied by g of x. Think of a business where one function models revenue and another models cost. Subtracting them gives you a new, useful function for profit. The essential point is that combining functions arithmetically is straightforward, but the new function is only defined where the original domains overlap. Let us cover the final two arithmetic operations for functions: division, which we call a quotient, and multiplication by a constant, known as scalar multiplication. The quotient of two functions, written as f over g, is found by simply dividing the value of f of x by the value of g of x. Its domain starts as the intersection of the individual domains, but with one crucial extra rule. We must exclude any x value that makes the denominator, g of x, equal to 0, because division by 0 is undefined. For instance, if g of x were x minus 2, we would have to exclude the value x equals 2 from the domain. Scalar multiplication is more straightforward. The function c times f is defined by multiplying the output f of x by the constant number circa. Since this does not introduce any new mathematical restrictions, the domain of c times f is identical to the original domain of f. The key takeaway is that division can shrink a domain, while scalar multiplication does not. Let us see how the domain of a new function is determined when we combine two existing ones, which is a crucial first step. First, we have the function f of x equals the square root of x. Because we can only take the square root of a non-negative number, its domain includes all real numbers greater than or equal to 0. Our second function, g of x, is the square root of the quantity 1 minus x. For its output to be a real number, the expression 1 minus x must be non-negative, which means that x must be less than or equal to 1. To create a combined function, any input x must be valid in both of these original functions, so we need the intersection, or overlap, of their domains. The only numbers that satisfy both conditions are those in the closed interval from 0 to 1. Therefore, the domain for the sum, difference, or product of f and g is this shared interval. Let us apply our rules for combining functions to a concrete example, which is essential for seeing how division uniquely affects the domain. I will use two functions. F of x equals the square root of x, and g of x equals the square root of 1 minus x. For their sum and product, the new domain is the intersection of their individual domains, which in this case is the closed interval from 0 to 1. However, for division, we must add an extra step. To find the domain of the fraction f over g, we start with that same interval, but must also exclude any x value that makes the denominator, g of x, equal to 0. Since g of 1 is 0, we must exclude the point 1, resulting in a domain from 0 up to but not including 1. Similarly, for g over f, we must exclude 0. Remember that when you divide functions, you must find the intersection of the domains, and then remove any values that make the denominator 0. Now that we know how to combine functions algebraically, we can also see what this looks like graphically. This is a visual way to understand the sum of two functions, f and g, by directly adding their graphs. The process is quite intuitive. For any input value that exists in the domains of both functions, we find the corresponding height, or STI value, on each graph. We then add these two heights together to get the height of the new graph for the function f plus g. For example, at the input value a, we take the height f of a and add the height g of a to find the new point on the combined graph. This method works for every single point within the shared domain, which is the intersection of the individual domains. The key takeaway is that the graph of a sum function is simply the vertical sum of the original function graphs. Here we can see a visual for the function combinations from our example, which helps clarify how their domains are determined. We have our two original functions, f of x, which is the square root of x, and g of x, which is the square root of the quantity 1 minus x. The graph for their sum, f plus g, is found by vertically adding the y values of the original two curves at every x value where they both exist. Similarly, the graph for the product, f times g, comes from multiplying those Grady values. Because the square root of x is only defined for x greater than or equal to 0, and the square root of 1 minus x is only defined for x less than or equal to 1, the combined functions can only exist on their overlapping domain. The essential thing to remember is that the domain of the combined functions is the intersection of the original domains, in this case the closed interval, from 0 to 1. Beyond simple arithmetic, we can combine functions through composition, which creates a chain where one function's output becomes another's input. This is called a composite function, written as f composed with g of x, and is defined as f of the quantity g of x. To evaluate it, we follow a two-step process. First, we find the output of the inner function, g of x. Second, we use that result as the input for the outer function, f. For this to be possible, the domain is restricted. An input x must be valid for the inner function g, and the output, g of x, must then be a valid input for the outer function f. Think of it like a factory where one machine makes a part and a second machine. The key idea is that we are nesting one function inside of another. Let us build some intuition for function composition by thinking of functions as machines. This diagram helps us visualize the process step by step. We begin with an initial input, x, which we feed into the first machine representing the function g. This machine processes x and produces a new value, the output, g of x. Now here is the key step of composition. This output, g of x, is not our final answer. Instead, it becomes the direct input for our second machine, which represents the function f. The function f then takes g of x and produces the final output, which we call f of g of x. Notice that even though we write f first in the notation f composed with g, the function g is the one that acts on the input first. So composition is simply a chain reaction, where one function's output becomes the next one's input. Let us apply our rules for composition to a concrete example, focusing on how to correctly determine the domain. First, I will find the formula for f composed with g of x by substituting the inner function, g of x, into the outer function, f. Since g of x is x plus 1 and f of x is the square root of x, the composition f of g of x becomes the square root of the quantity x plus 1. Now, to find the domain, we must ensure that the output of the inner function is a valid input for the outer function. The function g accepts any real number, but its output, x plus 1, must be a valid input for the square root function f. This means the quantity x plus 1 must be greater than or equal to 0. Solving this simple inequality shows that x must be greater than or equal to -1. The key takeaway is that a composite function's domain is restricted, so that the inner function's output lies within the outer function's domain. Let us continue with our example to see how changing the order of composition affects the outcome. First, we will find g composed with f of x, which means we apply f first and then g. The inner function is f of x, or the square root of x, which we substitute into g. Since g of x is x plus 1, our result is the square root of x plus 1. The domain for this new function is from 0 to infinity, which is inherited from the inner function f. Notice this is quite different from f composed with g of x, which highlights that the order of composition is critical. We can also compose a function with itself, as in f composed with f of x. Here, we take the square root of f of x, which gives us the square root of x, or x to the power of 1/4. The essential point is that the order of functions in a composition matters, and the domain is determined by the inner function. Let us start with one of the most straightforward ways to transform a function: shifting its graph vertically. This means we are moving every single point on the graph either straight up or straight down by the same amount. The formula for this is y equals f of x plus a constant, which we can call k. The rule is simple. If the constant k is greater than 0, the entire graph shifts up by that many units. If k is less than 0, the graph shifts down by the absolute value of k. For example, if our original function is the parabola y equals x squared, adding 1 to get y equals x squared plus 1 moves the entire parabola up 1 unit from the origin. Notice that we are adding the constant k directly to the function's output, f of x. So, to move a graph up or down, you simply add a positive or negative number to the function's formula. Now let us look at how to shift a graph horizontally, which involves adding a constant directly to the input variable x inside the function. The general formula for this transformation is y equals f of the quantity x plus h. The most important thing to watch for here is the direction of the shift, because it is the opposite of what you might first expect. When the constant h is positive, as in the function y equals the quantity x plus 3 squared, the entire graph actually moves to the left. Conversely, when h is negative, like in y equals the quantity x minus 2 squared, the graph shifts to the right. To remember this, think that adding a positive value to the input moves the graph left, while adding a negative value moves it to the right. Now that we have seen horizontal and vertical shifts separately, we can combine them to move a function's graph anywhere we want. This is a powerful way to build more complex graphs from simple parent functions. Let us start with the basic absolute value function, y equals the absolute value of x. To get the graph of y equals the absolute value of the quantity x minus 2, all minus 1, we perform two transformations in sequence. First, we look at the change to the input variable, x minus 2. This tells us to shift the entire graph 2 units to the right. Second, after that horizontal shift is complete, we apply the -1 at the end of the function. This shifts the resulting graph down by 1 unit. Following this order gives us the final, transformed graph. The main idea is that many complicated-looking functions are just simple ones that have been moved around the plane. Now that we have seen how addition shifts a graph, let us explore how multiplication can change its shape through scaling and reflecting. Scaling a graph means to either stretch or compress it, which we can do vertically or horizontally. This is accomplished by multiplying either the entire function or just the input variable x by a constant. For instance, multiplying the whole function by a value greater than 1, like 2, stretches the graph vertically, making it appear taller. Reflections are a special case of scaling, where the constant is -1. This operation flips the graph across an axis, creating a mirror image, without changing its fundamental shape. The key takeaway is that multiplying a function by a constant alters its proportions or orientation, unlike addition, which only changes its position. Now I will explore how multiplying a function by a constant scales, or resizes, its graph in the vertical direction. This transformation, called vertical scaling, happens when we multiply the entire function f of x by a constant circa. If the absolute value of c is greater than 1, every output value of the function gets larger, which stretches the graph vertically away from the x-axis. Conversely, if the absolute value of c is between 0 and 1, the output values get smaller, which compresses the graph vertically toward the x-axis. For instance, multiplying a sine wave by 2 doubles its amplitude, while multiplying by 1/2 cuts the amplitude in half. A very important special case is when c equals -1, which flips the sign of every output and reflects the entire graph across the x-axis. In short, multiplying the whole function by a constant controls its vertical size and orientation. Next, I will explain how multiplying the input variable x by a constant c can scale or reflect a graph horizontally. This transformation, written as y equals f of the quantity c times x, changes the graph's horizontal dimensions in a way that can seem counterintuitive. When the absolute value of SE is greater than 1, the graph is compressed horizontally, making it narrower. Conversely, when the absolute value of ASI is between 0 and 1, the graph is stretched horizontally, making it wider. For example, the graph of a function with an input of 2 times x will be squeezed to half its original width. A special and important case is when c equals -1, which results in y equals f of -x, and reflects the entire graph across the y-axis. The key takeaway is that multipliers inside the function's argument affect the graph horizontally, often in the opposite way you might first expect. Besides shifting a graph, we can also change its shape by stretching or compressing it vertically, a process known as scaling. This is accomplished by multiplying the entire function by a positive constant. When this constant is greater than 1, every y value gets larger, which stretches the graph vertically away from the x-axis. For instance, if our original function is the square root of x, multiplying it by 3 gives us y equals 3 times the square root of x, which makes the graph 3 times as tall at every x value. Conversely, multiplying by a constant between 0 and 1, such as 1/3, shrinks every xy value and compresses the graph vertically, pushing it toward the x-axis. The key thing to remember is that multiplying the entire function on the outside changes its vertical scale. Next, let us look at horizontal scaling, which changes a graph's width by multiplying the input variable x by a constant. This transformation can feel a bit counterintuitive because a multiplier greater than 1 actually compresses the graph. When we form the function y equals f of the quantity c times x, we reach each function value with a smaller x, effectively pulling the graph in toward the y-axis. For example, starting with y equals the square root of x, the function y equals the square root of the quantity 3 times x is compressed horizontally by a factor of 3. To stretch the graph, we divide the input by a constant, so y equals the square root of the quantity x divided by 3 stretches the graph by a factor of 3. Remember that to make a graph narrower horizontally, you must multiply the input variable by a number larger than 1. Let us see how a reflection works with a specific function, y equals the square root of x, and how it impacts the domain. To reflect a graph across the y-axis, we replace the input variable x with negative x, which transforms our function into y equals the square root of the quantity negative x. This change has a critical consequence for the domain. While the original function required x to be greater than or equal to 0, our new function requires the quantity negative x to be greater than or equal to 0. This condition is only met when x itself is less than or equal to 0. So do not assume the expression is undefined. It is perfectly valid for any non-positive x value. The key takeaway is that reflecting the graph across the y-axis also reflects its domain, in this case changing it from the interval starting at 0 to infinity to the interval from negative infinity up to and including 0. Now I will show you how to combine multiple transformations, like a compression and a reflection, into a single algebraic step. Our goal is to compress the graph horizontally by a factor of 2 and then reflect it across the y-axis. A horizontal compression by 2 means we replace the input x with 2x, and a reflection across the y-axis means we replace x with negative x. To perform both transformations on the input, we combine these effects and replace the original x with the quantity negative 2x. For our function, f of x equals x to the power of 4 minus 4x cubed plus 10, we make this single substitution. This gives us the quantity negative 2x to the power of 4 minus 4 times the quantity negative 2x cubed plus 10. After simplifying, we get the final equation. Y equals 16x to the power of 4 plus 32x cubed plus 10. The key is to determine the total effect on the input variable first, before performing the substitution. Now let us handle the second part of this example, which combines a vertical compression with a reflection across the x-axis. To achieve both effects at once, we will multiply the entire function f of x by a single constant. A vertical compression by a factor of 2 means we multiply by 1/2, and a reflection across the x-axis means we multiply by negative 1. Combining these, we multiply the entire function by negative 1/2. We start with y equals negative 1/2 times the quantity x to the power of 4 minus 4x cubed plus 10. Distributing this constant to each term inside gives our final formula. Y equals negative 1/2 x to the power of 4 plus 2x cubed minus 5. Remember that these vertical operations apply to the entire function output, not just the input x. Therefore, multiple vertical transformations can be performed together with a single multiplication. Now let us see how to combine two transformations that affect the input of our function: a horizontal compression and a reflection across the y-axis. To perform both of these actions, we must modify the input variable x before it is used in the function. First, to compress the graph horizontally by a factor of 2, we replace x with 2x. To then reflect it across the y-axis, we also multiply the input by negative 1. Combining these, we substitute the quantity negative 2x for every x in the original formula. This means our new function is y equals f of negative 2x, which expands to the quantity negative 2x to the power of 4 minus 4 times the quantity negative 2x cubed plus 10. After simplifying, this gives us the final equation shown on the graph. Y equals 16 times x to the 4th plus 32 times x cubed plus 10. Remember that all horizontal transformations are performed by changing the x value inside the function's parentheses. Now let us look at the second part of our example, which involves a vertical compression and a reflection across the x-axis. To achieve this, we will operate on the function's output, f of x, rather than its input. First, Compressing the graph vertically by a factor of 2 means we multiply the entire function by 1/2. Next, reflecting it across the x-axis means we multiply by -1. Combining these steps, we get a new function y, which is equal to -1/2 times the original function f of x. This results in the formula you see here. Y equals -1/2 x to the power of 4 plus 2x cubed minus 5. Notice how the original graph's shape has been flattened and flipped upside down. Remember that unlike horizontal transformations which alter the input x, these vertical transformations are applied to the entire output of the function. To wrap up, let us review the 4 main ways we can combine and transform functions to create new ones. First, we can perform standard arithmetic on functions, such as adding or multiplying them, where the new function's domain is the intersection of the original domains. Second, we can use composition, where the output of one function becomes the input for another, as in f composed with g of x, which equals f of g of x. For this to work, the inner function's output must be a valid input for the outer function. Third, we can shift a graph by adding a constant. Adding to the output moves it vertically, while adding to the input moves it horizontally. Finally, multiplying by a constant scales the graph vertically or horizontally, and using a negative constant reflects it across an axis. For example, starting with a simple parabola, these operations allow us to move, stretch, and flip it to fit a wide variety of shapes. The essential idea is that we can treat functions as building blocks, using these transformations to construct more sophisticated mathematical models. To wrap up, let us apply what we have learned with 2 review questions covering function composition and graph transformations. First, if f of x equals x squared and g of x equals the square root of the quantity x minus 1, what is the formula for the composite function f composed with g of x, and what is its domain? Remember to first find the new function by substitution, and then carefully determine the domain based on the input restrictions of both the inner function and the final result. Second, can you describe the sequence of transformations that turns the graph of y equals the absolute value of x into the graph of y equals -3 times the absolute value of the quantity x plus 4, all minus 2? Think step by step about the shift, stretch, reflection, and final shift. I encourage you to pause and work through these problems to check your understanding.